Hello, this is a presentation on the Seven Bridges of Königsberg by Isaiah Bochter. A little history background of the Seven Bridges of Königsberg. This was a problem solved by Leonhard Euler in 1735. Euler learned of this problem of the bridges in Königsberg through a colleague called Carl G. Eller. Eller was a correspondent of Heinrich Kuhn, the Polish mathematician, one of the greatest mathematicians of the 18th century. And Euler was commissioned to find the mathematical solution behind a reason problem of something that became known as the geometry of position. So first, to understand what this means, we have to first look at what are graphs in math. So normally people think of graphs as an X and Y axis, or X, Y, and Z axes. And there are two meanings for graphs in math. There's that, and then there's this is what we see, which is the definition of it or that they have one or more vertices connected by edges. So as you can see here, the vertices are the little circles that are lettered in the left example, and the edges are the lines. In other industries such as engineering and medicine, these are known as networks. So this is the problem this is the problem of the bridges of Königsberg that Euler was commissioned with. As you can see here, there are 7 bridges and 4 areas of land. And basically what this depicts is the real city of Königsberg, where there was an island surrounded by bridges. And as you can see here, these are rivers. And so to connect from each mainland to each bridge, to each mainland to each mainland, there were bridges. And so Euler was commissioned to figure out how he can get through every single bridge without crossing himself over again. And he was, obviously, as you can see, by reason, that is impossible. For example, you could take from bridge A to C, to E, to D, to G, to J. But that's impossible because you can't go through B and then back to E. You would have to cross through E and then choose J, for example. You would always have to leave out at least one of these bridges. And so Euler was commissioned to figure out mathematically why that is impossible. So here's the process. First, you have to draw the bridges as a graph, which, the vertices, which are the land masses with capital letters, and the edges, which are the bridges with lowercase letters. So as you can see in this graph, this is what Königsberg, this is what the bridges look like. As you can see, you have the landmass here, which is the island. You have the 2 mainlands and the second island. And these are all bridges connecting between them. So next you have to create a table, and you have to have a column for the vertices and a column for the number of bridges coming from that vertex. So for example, as you see here in A, you have the vertex and you have 1, 2, 3, 4, 5 bridges coming out of vertex A. And you should also have a column for the times a region must appear. And you take that by taking the bridges coming from each vertex, which is what we just calculated, and you divide that by 2. And all decimal answers are rounded up. So basically all odd numbered bridges will round up 1. And then you have to solve it. So what you do is you add the number of times that each region must appear, and the journey is possible when the regions equals the amount of bridges plus 1. Like the amount of times that the region will show up has to equal the bridges plus 1. It is not possible when that is not true. So as you can see here from that example, you have the regions, you see A, B, C, and D. And A has 5 bridges coming out of it, B has 3, C has 3, and D has 3. So to find the times the region must appear, you have to divide all of those by 2. And because those are all odd numbers, they all round up 1. And so as you can see at the top, the number of bridges in total is 7. So the number of bridges plus 1 is 8. And so when you add up all of these, all of the times a region must appear, you get 9, which is more than 8, which means that the journey is impossible, that you're going to be missing out one of the bridges. So here's another example problem that is shown. This has 2 islands on it, 4 pieces of land. It has 4 rivers, and it has 15 bridges. And this was also published by Euler in his analysis of the geometry of position. And so here's a graph of it. I know it's a little sketchy, but that's because I had to use Microsoft Paint to create it. So as you can see, you have the five land masses from here. You have A, B, C, this, which is D, and E, and F. And so you have all these bridges connecting between them. You have 15 of them in this picture. And so the process is that you have to do the same thing as you did. You have the number of bridges and the number of bridges plus 1. So as you can see, there are a lot of even number bridges here. And these even number bridges just divide by 2 to even numbers, and the odds have to round up by 1. So if you notice a pattern, there are 2 numbers that are odd, 2 regions that are odd. And that is because one region is for entrance and one region is for exit. And so those have to be odd. And so that's just like, you know, like a shortcut that you have, if you have 2 even and the rest are odd, then most likely it will be possible. As you can see, as you add the number of times the region must appear, it equals 16, which is equal to the number that we desire. So in conclusion, Leonhard Euler published his results into Solutu problematis ad geometrion situs perientes, which means the solution of a problem relating to the geometry of position. And this problem went on to found topology in graph theory. Topology is the study of the surfaces of shapes, of 3D shapes, in graph theory, which is what we just went over, which is the networking, basically. That's all. Thank you.